Imagine, for a moment, the world as a continuous stream of sensory input, sights, sounds, textures, and emotions all flowing in simultaneously. How does a conscious being make sense of this flood of data? The first layer of the unified meta-theory of cognitive-symbolic systems, UMT, addresses this through the consciousness relativity theory, CRT, which models perception as a predictive, hypothesis-driven process. Instead of passively receiving information, CRT proposes that the mind actively generates expectations about what it will perceive and continuously updates these expectations in response to incoming signals. This allows organisms, or even artificial systems, to efficiently filter noise, detect anomalies, and stabilize their perceptual experience. Linked closely with CRT is the differentiated representation theory, DRT, which explains how the raw perceptual stream is parsed into hierarchical and differentiated mental categories. DRT shows how the mind forms abstract concepts by recursively subdividing patterns of input, creating increasingly refined categories that serve as the scaffolding for higher-level reasoning. When combined, CRT and DRT provide a foundation for structured cognition. CRT predicts what is likely to occur, DRT organizes those predictions into meaningful categories, and together they produce a continuously evolving mental model of reality. In practice, this framework can be applied to everything from enhancing human learning, helping students identify assumptions and biases, to designing AI perception systems that can anticipate errors, adapt to uncertainty, and process complex sensory environments efficiently. By grounding cognition in these predictive and differentiative principles, Part 1 of UMT establishes the essential first step in transforming raw experience into knowledge, and it sets the stage for deeper integration, reasoning, and communication. Once perception is structured and concepts are formed, the next challenge is integration. How disparate pieces of information, predictions, and categories come together into coherent cognitive states. This is where the modular cognitive architecture, MCA, comes into play. MCA models the mind, or an artificial system, as a network of specialized modules that each process specific aspects of information, yet remain interconnected to enable global coherence. This allows for simultaneous attention to multiple streams of data, hierarchical problem-solving, and dynamic allocation of cognitive resources. Through MCA, one can explain phenomena such as multitasking, flow states, and even dissociation when integration fails. Building upon MCA is the montage-based epistemic model, MEM, which formalizes how integrated information becomes structured knowledge. MEM is a framework for hypothesis formation, analogical reasoning, conceptual blending, and belief revision. It transforms the modular outputs from MCA into epistemic frames that can be tested, communicated, and refined. In practice, MEM allows both humans and AI to construct explanatory models of the world, compare competing theories, and adjust beliefs in response to new evidence. Together, MCA and MEM provide the engine for higher-order cognition. They take structured perceptions and categories, integrate them across functional modules, and translate them into internally coherent theories and hypotheses. This integrated stage is essential for learning, creative problem-solving, and scientific discovery, and it forms the bridge between individual cognitive processes and the broader sharing of knowledge that UMT enables. Once knowledge is formed internally, it must be expressed, shared, and propagated to have real-world impact. This is the domain of the Symbolic Communication System, SCS, the fifth layer of UMT, which models how internal epistemic frames are translated into external symbols, whether language, diagrams, formal logic, or multimodal representations. SCS formalizes communication as a multi-stage pipeline, selecting the right concepts to convey, encoding them into symbolic forms, structuring them into coherent messages, contextualizing for the receiver's knowledge and culture, transmitting through a medium, and finally, interpreting on the other end. This layer captures not only human communication, but also interactions between humans and between AI systems themselves. Crucially, SCS preserves semantic content, structural relations, and pragmatic intent, while accounting for ambiguity, noise, and interpretive variation. Building on SCS is the modular publishing theory, MPT, the sixth layer of UMT, which formalizes how symbolic content is distributed, versioned, collaboratively refined, and integrated into shared cultural structures. MPT treats culture as a distributed cognitive system. Symbolic artifacts, communication protocols, and collaborative practices become the scaffolding for collective intelligence. Through MPT, knowledge is not static but evolves dynamically across populations, digital platforms, and institutions, enabling cumulative cultural evolution. Together, SCS and MPT close the loop of cognition. Internal theories and beliefs become externalized, shared, and refined, feeding back into perception, attention, and epistemic reasoning, and allowing both individuals and collectives to learn, adapt, and innovate. The Unified Metatheory, UMT, is not merely a theoretical framework. It is designed for practical application across diverse domains, from artificial intelligence to education, healthcare, and governance. In AI, UMT provides a blueprint for building systems that are interpretable, self-monitoring, and epistemically transparent. CRT modules enable uncertainty-aware perception. MCA structures allow modular integration and reflective reasoning. MEM supports theory building and belief revision. SCS translates internal states into symbolic explanations, and MPT ensures collaborative learning and version knowledge management. Such systems can learn from their environment, communicate internally and externally, and refine their models in ways that mirror human collective intelligence. In education, UMT offers a framework for teaching students not only knowledge but metacognition. CRT cultivates awareness of assumptions and biases. DRT models conceptual differentiation. MCA strengthens attentional control and flow-state learning. MEM develops reasoning and theory-building skills. SCS enhances communication and articulation. And MPT facilitates collaborative knowledge creation through projects, peer review, and digital portfolios. In healthcare, UMT layers provide diagnostic and therapeutic insight. CRT explains perceptual distortions like anxiety or depression. MCA illuminates integration failures seen in dissociation or PTSD. MEM aligns with cognitive therapies through frame revision and belief reweighting. SCS improves patient-clinician communication and empathy. And MPT structures institutional knowledge for better procedural and interdisciplinary collaboration. Finally, in governance and policy, UMT enables transparent decision-making. CRT identifies perceptual biases in decision-makers. MEM guides adaptive policy modeling and scenario testing. SCS ensures clarity and trust in public communication. And MPT preserves institutional memory and supports collaborative drafting and knowledge sharing. Across these domains, UMT transforms individual cognition into collective intelligence, offering a unified architecture for both human and artificial systems to learn, adapt, and co-evolve. A crucial strength of the Unified Metatheory, UMT, is that it is empirically testable. Each layer of the framework generates predictions that can be validated across neuroscience, psychology, artificial intelligence, communication studies, and sociocultural analysis. For CRT, we can measure prediction error signals in EEG, track top-down modulation in fMRI, and assess attentional stability under varying noise conditions, providing insight into how perception is shaped by prior beliefs. DRT predictions can be tested through developmental studies, observing hierarchical concept formation and category differentiation, or in AI through unsupervised structure learning and hierarchical generative modeling. MCA can be validated by measuring global workspace ignition events, modular specialization, and stress-modulated memory consolidation using EEG and fMRI, while behavioral experiments can test multitasking, flow states, and dissociation. MEM's predictions, such as patterns in hypothesis formation, analogical reasoning, belief revision, and conceptual blending, can be explored through cognitive tasks in humans, neural symbolic reasoning in AI, and multi-agent simulations. SCS predictions about comprehension, ambiguity resolution, and metaphor processing can be measured in linguistics and psychology, while AI implementations test explainable symbolic communication and multimodal translation. Finally, MPT predictions about versioned cultural evolution, mimetic propagation, and collaborative knowledge building can be examined using citation networks, open-source ecosystems, and multi-agent distributed learning simulations. By running real-time multi-agent simulations, we can observe how agents CRT, DRT, MCA, MEM, SCS, and MPT layers interact, how beliefs and symbolic messages propagate, how consensus emerges or fails, and how diversity of internal hypotheses evolves. These simulations provide a sandbox where UMT is not merely theoretical, but actively generating insights, revealing emergent behaviors, cultural knowledge dynamics, and the mechanisms through which individual cognition scales into collective intelligence. Running simulations and empirical tests using the UMT framework provides a deep well of insights into cognition, communication, and culture. From these experiments, we can observe how individual perception, CRT, and conceptual differentiation, DRT, combine with attentional integration, MCA, to shape the formation of internal hypotheses, MEM. We can measure how effectively these hypotheses are translated into symbolic communication, SCS, and how they are consolidated and transmitted through cultural systems, MPT. These simulations reveal patterns in consensus formation, the maintenance of hypothesis diversity, and the emergence of cultural norms. They also show how feedback loops operate. Cultural knowledge stored in MPT influences CRT priors, which in turn affect DRT, MCA, and MEM processes, highlighting the recursive, dynamic nature of cognition and culture. For AI, UMT provides a blueprint for building systems that are interpretable, adaptive, and capable of collaborative knowledge generation, where agents not only process information but also reason, revise theories, and communicate insights in human-understandable forms. For education, healthcare, and governance, UMT informs interventions that enhance metacognition, improve communication, and foster collective problem-solving. Looking ahead, future directions include scaling multi-agent simulations to more complex networks, integrating richer symbolic languages, modeling cross-cultural dynamics, and implementing hybrid human-AI cognitive systems. Each step provides measurable outputs, allowing us to refine the theory, test its predictions, and explore how cognition, communication, and culture co-evolve. UMT is therefore not only a theoretical framework, but a practical platform for understanding and shaping intelligence, both individual and collective, in ways that were previously inaccessible. The Unified Metatheory, UMT, is not just an abstract framework, it is directly actionable across multiple domains. In artificial intelligence, UMT can guide the creation of explainable, adaptive, and collaborative systems. For instance, CRT-inspired modules allow AI to estimate uncertainty and anticipate perceptual errors, while MCA-inspired architectures support modular integration of diverse inputs. MEM provides a structure for AI to generate, revise, and maintain competing hypotheses, enabling more sophisticated reasoning and scientific discovery. SCS ensures that AI systems can communicate their internal reasoning clearly, adapting explanations to different audiences, and MPT enables collaborative knowledge accumulation, allowing AI to participate in versioned, cultural-scale learning systems. In education, UMT informs teaching methods that foster metacognition and collaborative learning, helping students not just absorb information, but understand the dynamics of their own cognition, reasoning, and communication. Healthcare applications benefit by mapping patient cognition onto UMT layers. Perceptual biases, fragmented reasoning, and maladaptive beliefs can be modeled and addressed systematically, while SCS and MPT layers support better patient, clinician communication, and institutional knowledge retention. Governance and policymaking also leverage UMT. By modeling perception, reasoning, communication, and cultural propagation, decision-makers can identify cognitive biases, evaluate policy scenarios rigorously, communicate clearly to the public, and maintain an evolving institutional memory. Across all domains, UMT enables a shift from reactive, ad hoc processes to a principled, theory-driven approach, where cognitive, epistemic, and cultural dynamics are measured, guided, and optimized. By operationalizing each layer, practitioners gain tools to simulate, predict, and enhance the interplay of individual reasoning and collective intelligence, ultimately improving decision quality, transparency, and adaptability in complex real-world systems. The unified meta-theory opens profound possibilities for human-AI coevolution, where cognitive systems are no longer isolated but intertwined. By mapping perception, consciousness, epistemic reasoning, communication, and cultural propagation into a single framework, UMT allows humans and AI to collaborate in shared cognitive spaces. CRT modules can help AI anticipate human perceptual errors and attentional limitations, while MCA-inspired architectures allow AI to integrate human inputs alongside machine-generated data dynamically. MEM enables both humans and AI to construct, test, and revise hypotheses collectively, while SCS ensures that symbolic reasoning is communicated transparently, reducing misinterpretations between human and machine collaborators. MPT extends this collaboration into cultural-scale knowledge accumulation, where contributions from multiple agents, human and AI, are versioned, integrated, and made reusable for future reasoning. The implications are vast. Scientific research can become faster and more rigorous. Education can be personalized while still supporting shared learning, and organizational or societal decision-making can benefit from a harmonized cognitive ecosystem. Future research can explore adaptive UMT layers, where AI learns not only from human inputs but also from evolving cultural dynamics, while humans can leverage AI-driven simulations to refine understanding of their own cognition and collective behavior. Ultimately, UMT provides a roadmap for building integrated cognitive ecosystems, where humans and machines enhance each other's reasoning, learning, and cultural impact, creating an unprecedented opportunity for coevolutionary growth. While the unified meta-theory provides a comprehensive framework for modeling cognition, communication, and cultural evolution, it is not without limitations and challenges. First, the complexity of implementation is significant. Integrating 6 interacting layers, CRT, DRT, MCA, MEM, SCS, and MPT, requires enormous computational resources, sophisticated modeling, and careful calibration to prevent cascading errors. Second, validation across domains remains a challenge. While simulations can illustrate UMT dynamics, empirically verifying predictions in humans, organizations, or hybrid human-AI systems requires carefully designed experiments spanning neuroscience, psychology, education, and sociocultural studies. Third, scalability and interpretability may be difficult. As systems grow, maintaining clarity about the propagation of beliefs, hypotheses, or cultural knowledge becomes increasingly complex, raising questions about trust, reliability, and transparency. Fourth, ethical considerations are paramount. Deploying UMT-based AI in real-world contexts could influence human beliefs, cultural norms, or decision-making in ways that are unintended or manipulative. Careful attention must be paid to consent, bias mitigation, and safeguarding autonomy. Moreover, the feedback loops between MPT and CRT highlight the potential for cultural reinforcement of certain priors, which could exacerbate groupthink or entrench misinformation if not carefully monitored. Finally, interdisciplinary collaboration is essential. The theory's success depends on input from cognitive scientists, AI researchers, ethicists, and social theorists to ensure that its implementation is responsible, accurate, and aligned with human values. Despite these challenges, acknowledging limitations early allows UMT to evolve responsibly, offering both theoretical insight and practical guidance while avoiding misuse or overreach. Looking forward, The unified meta-theory offers a vision for how cognitive scientific understanding and technology could transform society. At the individual level, UMT provides tools for enhanced self-awareness, learning, and decision-making. CRT modules could improve perceptual accuracy and attentional control. DRT structures could support deeper conceptual understanding. MCA mechanisms could optimize focus and integrate complex information. MEM systems could enable rigorous reasoning and belief revision. SCS layers could enhance communication, explanation, and collaboration. And MPT processes could allow individuals to contribute meaningfully to collective knowledge. At the societal level, UMT offers a blueprint for collective intelligence, in which cultural knowledge is systematically captured, versioned, distributed, and refined. Scientific communities could leverage UMT-based AI to test competing hypotheses, integrate research findings across disciplines, and accelerate discovery. Educational systems could implement layered UMT simulations to teach students not only content, but the cognitive architectures that underlie reasoning and creativity. Healthcare could benefit from predictive and adaptive cognitive models for diagnostics, therapy, and institutional memory, while governance could use UMT to improve policy transparency, scenario planning, and participatory decision-making. Beyond structured institutions, UMT could influence digital ecosystems, social platforms, and AI-human hybrid networks, fostering cultural evolution that is deliberate, measurable, and ethically guided. The vision is one where human and artificial cognition are not separate streams, but interconnected, feedback-driven systems, capable of learning, reasoning, and evolving together. Ultimately, UMT represents a roadmap for a society in which knowledge, communication, and culture are fully integrated, enabling both individual growth and collective progress on an unprecedented scale. Having outlined the conceptual and societal potential of UMT, we now turn to practical demonstrations and simulations that bring the theory to life. UMT is not merely abstract. It can be implemented in multi-agent simulations, AI systems, and human-AI hybrid experiments. For instance, the CRT layer can be modeled in computational agents as a predictive perception module, allowing agents to estimate uncertainty, detect anomalies, and adapt their perceptual priors over time. The DRT layer can be tested using hierarchical clustering or recursive differentiation algorithms, showing how agents form increasingly complex conceptual categories. MCA can be simulated through attention-based integration and metacontroller architectures, demonstrating how modular processes combine information and prioritize tasks. MEM provides a framework for theory-building agents. Simulations can show how agents generate hypotheses, revise beliefs under contradictory evidence, and perform analogical reasoning. SCS allows these internal states to be translated into symbolic messages, which can then be evaluated for communication fidelity, ambiguity resolution, and interpretability. Finally, MPT enables agents to record, distribute, and version their symbolic knowledge, creating cultural memory graphs that can be analyzed for consensus, diversity, and propagation patterns. Running these simulations allows us to observe emergent behaviors, measure cognitive dynamics, and refine the theory itself. For example, we can test how different network structures, agent connectivity, or noise levels affect the convergence of cultural knowledge, or how individual agents' internal diversity impacts collective problem-solving. These simulations turn UMT from a theoretical framework into a laboratory for exploring cognition, communication, and cultural evolution, providing tangible insights into both individual and collective intelligence. Once we begin running simulations based on the UMT framework, the theory begins to teach us about itself. By observing how agents interact across CRT, DRT, MCA, MEM, SCS, and MPT layers, we see patterns emerge that are not immediately apparent from theory alone. For instance, CRT-based predictive perception in agents highlights how uncertainty and attentional gating shape not only individual learning, but also the flow of information through the network. DRT simulations reveal how hierarchical differentiation creates conceptual scaffolds that facilitate complex reasoning, while MCA shows the importance of modular attention and task prioritization for maintaining coherent cognition under noisy conditions. MEM-driven simulations demonstrate the power of hypothesis generation and belief revision. We can watch agents maintain multiple competing theories and evaluate how they converge or fail to converge through analogy and causal inference. SCS provides a window into symbolic communication, showing how encoding and decoding processes influence the fidelity and interpretability of shared knowledge. MPT simulations make it clear that cultural memory and version knowledge are crucial for collective intelligence. The structure of connections, modularity of contributions, and diversity of perspectives all affect the stability and adaptability of cultural knowledge. By analyzing these simulations, we can measure key metrics, such as communication fidelity, hypothesis diversity, and consensus formation, and identify interlayer interactions that amplify or inhibit learning. These practical experiments transform UMT from an abstract architecture into a dynamic, self-refining system, showing us how cognition, communication, and culture evolve together in both artificial and human settings. With a firm grasp of how the UMT framework operates and what we learn from simulations, the next step is to explore practical applications across multiple domains. In artificial intelligence, UMT provides a blueprint for explainable, adaptive, and collaborative systems. CRT allows AI to maintain uncertainty-aware perception, giving machines a kind of self-monitoring awareness. DRT helps structure hierarchical concept formation, enabling AI to categorize and abstract information in human-like ways. MCA offers modular integration, allowing AI to coordinate multiple inputs and tasks efficiently, even under noisy conditions. MEM empowers AI to construct hypotheses, revise beliefs, and generate analogical reasoning, forming the backbone of theory building and scientific discovery systems. SCS ensures that these insights can be communicated clearly, making AI explainable to humans through symbolic translation, contextualization, and pragmatic inference. Finally, MPT enables collaborative knowledge management, version learning, and shared cultural memory, creating a foundation for AI that can participate meaningfully in human knowledge networks. Beyond AI, UMT can transform education by teaching students how to think, not just what to memorize. Each layer corresponds to a cognitive skill. CRT fosters metacognitive awareness, DRT develops conceptual differentiation, MCA enhances attentional control, MEM promotes reasoning and evidence evaluation, SCS cultivates communication, and MPT supports collaborative knowledge creation. In healthcare, UMT offers a diagnostic and therapeutic lens. CRT explains perceptual distortions, MCA highlights integration failures, MEM aligns with belief revision therapies, SCS improves patient-clinician communication, and MPT structures institutional knowledge. In governance and policy, UMT provides a framework for transparent, evidence-based decision-making, where collective epistemology, policy reasoning, communication, and institutional memory are systematically integrated. By applying UMT in these domains, we can bridge cognition, communication, and culture, demonstrating that the framework is not only a theoretical construct, but a practical tool for advancing human and artificial intelligence alike. Looking forward, the unified metatheory, UMT, opens a vast landscape for empirical exploration and practical experimentation. One immediate direction is testing the predictions of each layer. CRT can be examined through perceptual and attention-based experiments, DRT through hierarchical concept development studies, MCA via neural and behavioral measures of integration and modularity, MEM through reasoning, analogy, and belief revision tasks, SCS through communication fidelity and ambiguity resolution tests, and MPT through modeling cultural evolution and collaborative knowledge systems. Multi-agent simulations, as we've already explored, allow us to observe interactions across layers, measure cultural consensus, hypothesis diversity, and communication fidelity, and test how internal cognitive processes propagate into shared symbolic structures. Advances in neuroscience, AI, and social modeling provide concrete platforms for this. Predictive coding networks can embody CRT, hierarchical generative models can realize DRT, attention-based neural architectures can implement MCA, neural symbolic agents can explore MEM dynamics, explainable AI can demonstrate SCS principles, and distributed multi-agent systems can instantiate MPT. Moreover, UMT suggests cross-layer empirical studies, such as how cultural knowledge, MPT shapes perception, CRT, or how theory building, MEM, influences communication, SCS. Beyond laboratory and simulation, UMT provides a roadmap for real-world applications, from adaptive learning platforms to collaborative AI research systems, and from clinical interventions to policy modeling. Each experiment, each simulation, each real-world deployment offers not only validation, but insight into the mechanics of cognition, communication, and culture, turning the UMT framework into a living, evolving tool for both understanding and designing intelligent systems. Integrating the unified metatheory into human and artificial systems requires both conceptual clarity and engineering precision. Each UMT layer can serve as a modular component in larger cognitive architectures. For humans, UMT can guide metacognitive training, teaching students to monitor perception, CRT, differentiate concepts, DRT, coordinate attention and modular processing, MCA, build and revise theories, MEM, communicate ideas effectively, SCS, and collaborate on shared knowledge, MPT. For AI, these same layers provide a blueprint for building explainable, adaptive, and socially aware systems. Predictive perception modules emulate CRT. Hierarchical representation learning implements DRT. Attention-driven modular networks realize MCA. Neural symbolic reasoning frameworks embody MEM. Symbolic explanation interfaces reflect SCS. And version knowledge graphs enable MPT-like cultural learning. By designing systems that mirror the interconnected dynamics of human cognition, we can create AI agents capable of learning, reasoning, and collaborating in ways that are transparent, interpretable, and aligned with human values. Moreover, integrating UMT across human, AI teams facilitates hybrid intelligence, where human insight and machine efficiency synergize. Simulations, multi-agent experiments, and real-world deployments can iteratively refine both theoretical models and practical architectures, enabling UMT not only as a descriptive framework, but as a prescriptive guide for building next-generation cognitive systems that scale from individual reasoning to cultural knowledge propagation. The unified metatheory, UMT, extends far beyond theoretical modeling, offering actionable insights across multiple domains. In education, UMT provides a framework for cultivating metacognitive and collaborative learning. CRT trains students to become aware of perceptual and cognitive biases. DRT guides the construction of conceptual hierarchies. MCA enhances attentional control and cognitive coordination. MEM encourages hypothesis-driven reasoning and reflective thinking. SCS strengthens communication and expression, and MPT enables collaborative knowledge building through versioned, shareable projects. In healthcare, UMT offers a lens for diagnosing and treating cognitive and perceptual disorders. CRT informs interventions targeting anxiety, depression, or trauma by identifying maladaptive priors. DRT models the evolution of distorted conceptual frameworks. MCA helps understand integration deficits in conditions such as ADHD or dissociation. MEM provides a basis for therapeutic approaches like cognitive restructuring and narrative therapy. SCS supports patient-clinician communication, and MPT structures institutional memory, enhancing procedural consistency and interdisciplinary collaboration. In artificial intelligence, UMT guides the development of explainable, adaptive, and culturally aware systems. CRT modules enhance uncertainty-aware perception. DRT architectures support hierarchical concept formation. MCA networks manage attention and modular integration. MEM frameworks enable causal reasoning and theory building. SCS ensures interpretable symbolic communication, and MPT facilitates distributed knowledge sharing among AI agents. In governance and policy, UMT empowers transparent, evidence-based decision-making. CRT identifies perceptual and cognitive biases in decision-makers. DRT structures complex policy concepts. MCA supports integration across multiple inputs. MEM allows hypothesis testing and scenario evaluation. SCS enables clear public communication. And MPT maintains institutional knowledge, version policies, and collaborative drafting. Across all these domains, UMT provides a holistic, scalable framework that aligns perception, cognition, communication, and culture, enabling individuals, institutions, and intelligent systems to learn, reason, and evolve in coordinated, measurable ways. A central strength of the unified metatheory, UMT, lies in its empirical testability. Each layer, CRT, DRT, MCA, MEM, SCS, and MPT, generates precise predictions that can be validated through neuroscience, psychology, artificial intelligence, and sociocultural analysis. For CRT, experiments can examine prediction error signals in the brain, attentional stability under varying sensory noise, and perceptual robustness in AI systems with uncertainty-aware perception modules. DRT predictions can be tested through developmental studies of hierarchical concept formation, infant category learning, and unsupervised AI models that self-organize conceptual hierarchies. MCA can be explored via EEG and fMRI studies that capture global workspace activation, attention modulation, and modular integration, alongside AI simulations using metacontroller architectures to manage multi-input integration. MEM offers a framework for studying hypothesis formation, analogical reasoning, belief revision, and conceptual blending, both in human cognition and in AI agents designed for causal inference and theory building. SCS predictions are empirically approachable through linguistic experiments, comprehension studies, and multimodal AI systems that test symbolic translation, interpretability, and context-sensitive reasoning. Finally, MPT can be assessed through computational social science, analyzing version cultural evolution, mimetic propagation, and collaborative knowledge networks in both human societies and multi-agent simulations. By combining computational simulations, experimental neuroscience, and behavioral studies, UMT not only provides a descriptive model of cognition and culture, but also a framework for generating actionable, measurable, and falsifiable insights across domains. One of the most powerful aspects of the unified metatheory is its ability to capture cross-layer dynamics, revealing how different cognitive and cultural processes interact to produce emergent phenomena. The layers do not operate in isolation. CRT influences MCA by modulating attentional focus and perceptual priors, which in turn affect how conscious content is integrated. MCA shapes MEM by determining the density and structure of integrated content, influencing which hypotheses are formed, retained, or revised. MEM informs SCS by providing the structured epistemic frames that guide symbolic expression, ensuring that messages are coherent and meaningful. Likewise, SCS feeds MPT, transforming individual symbolic communication into modular cultural artifacts that can be distributed, versioned, and collectively refined. Feedback loops also exist. MPT feeds back into CRT and DRT as cultural priors and institutionalized knowledge shape perception and conceptual differentiation. These interactions produce emergent properties, such as collective intelligence, distributed problem-solving, and cultural evolution. By modeling cognition as a layered, interconnected system, UMT enables researchers to simulate, predict, and manipulate complex cognitive and cultural dynamics, bridging individual perception, internal reasoning, communication, and societal knowledge in a single formal framework. The unified metatheory is not just a theoretical construct. It is directly applicable across multiple domains where cognition, reasoning, and communication play critical roles. In artificial intelligence, UMT provides a blueprint for building systems that are not only predictive and adaptive, but also epistemically transparent and explainable. CRT modules can generate uncertainty-aware perceptions. MCA supports modular integration and reflective reasoning. MEM allows for hypothesis generation and belief revision. SCS ensures symbolic communication, and MPT structures knowledge collaboratively across multi-agent systems. In education, UMT empowers learners to develop higher-order cognitive skills rather than mere rote memorization. CRT teaches metacognitive awareness. DRT enables concept differentiation. MCA develops attentional control and flow states. MEM fosters reasoning and theory building. SCS enhances communication and expression, and MPT allows collaborative knowledge creation and peer review processes. In healthcare, UMT offers a multi-layered diagnostic framework. CRT can highlight perceptual distortions contributing to anxiety or trauma. MCA identifies integration failures seen in dissociation or ADHD. MEM supports cognitive and narrative therapies. SCS facilitates patient-clinician communication. And MPT organizes institutional knowledge to improve interdisciplinary collaboration. In governance and policymaking, UMT guides transparent, adaptive, and evidence-driven decision-making. CRT reveals perceptual biases. MEM enables scenario modeling and multi-theory evaluation. SCS ensures clear public communication, and MPT structures institutional memory and collaborative drafting. By providing a comprehensive architecture from perception to cultural impact, UMT demonstrates how a unified theory of cognition can transform real-world problem-solving, learning, and societal decision-making. A crucial strength of the unified meta-theory is its empirical testability. Each layer, CRT, DRT, MCA, MEM, SCS, and MPT, generates predictions that can be systematically evaluated in neuroscience, psychology, artificial intelligence, and sociocultural research. For CRT, experiments can probe predictive perception, top-down modulation, and attention under uncertainty, while psychological tests measure susceptibility to illusions or attentional stability. DRT's hierarchical differentiation can be observed through developmental studies, infant cognition experiments, and cortical feature mapping. MCA's predictions of conscious integration, global workspace ignition, and stress-modulated modular activity can be studied using EEG, fMRI, and intracranial recordings. MEM allows empirical tracking of hypothesis formation, analogical reasoning, and belief revision, with corresponding neural correlates in hippocampal and prefrontal networks. SCS provides testable predictions in linguistics, pragmatics, and symbolic reasoning, measurable through comprehension studies and AI-based translation experiments. MPT, finally, can be examined through cultural dynamics, open-source collaboration networks, citation patterns, and mimetic propagation simulations. Beyond individual layers, UMT supports multi-layer simulations. Agents with integrated CRT-MCA-MEM-SCS-MPT architectures can be modeled to study how perceptual, cognitive, and cultural processes interact. Simulations track metrics like communication fidelity, hypothesis diversity, and cultural consensus, visualizing how internal cognitive states translate into shared symbolic knowledge. These empirical approaches, both experimental and computational, ensure that UMT is not just conceptual. It is a framework that can learn from data, adapt, and provide actionable insights about cognition, culture, and artificial intelligence. Any of the most powerful aspects of the unified meta-theory is its focus on cross-layer interactions and the feedback loops that emerge between perception, cognition, symbolic reasoning, and culture. The theory posits that each layer, CRT, DRT, MCA, MEM, SCS, and MPT, does not operate in isolation. Instead, there are continuous reciprocal influences. CRT shapes the initial perceptual priors that feed into DRT's conceptual differentiation, which in turn informs MCA's integrative processes. MEM then uses this integrated content to form and revise hypotheses, generating epistemic frames that are encoded by SCS into symbolic messages. These messages propagate through MPT into cultural structures, which subsequently influence new perceptual priors in CRT, completing a cognitive cultural loop. Simulations show that these feedback loops can amplify learning, stabilize consensus, or maintain diversity depending on the parameters of interaction. For example, high-fidelity communication between MEM and SCS promotes shared understanding, while increased hypothesis diversity in MEM sustains creative exploration. These dynamics illustrate that UMT is not just a linear pipeline, it is a complex adaptive system, where emergent behaviors arise from the interplay of modular yet interconnected layers. By explicitly modeling these interactions, UMT allows researchers to study how individual cognition scales to collective intelligence, how cultural norms evolve, and how artificial agents might integrate human-like reasoning with collaborative knowledge creation. UMT offers a comprehensive blueprint for designing AI systems that are both interpretable and cognitively aligned with human reasoning. At the foundational level, CRT can be implemented as predictive perception modules, enabling AI to model uncertainty, detect anomalies, and generate confidence-weighted predictions. DRT provides the AI with hierarchical conceptual differentiation, allowing it to organize sensory input and knowledge representations into structured, multi-level frameworks. MCA equips AI with modular integration and attention mechanisms, supporting multi-agent coordination, task prioritization, and dynamic focus switching. MEM enables AI to generate, test, and revise hypotheses, facilitating analogical reasoning, causal inference, and adaptive theory building. SCS then transforms these internal cognitive processes into symbolic explanations, producing outputs that are interpretable by humans, adaptable to context, and capable of resolving ambiguity. Finally, MPT governs the versioning, distribution, and integration of knowledge across AI systems, creating collaborative learning environments where knowledge is refined iteratively. Together, these layers allow AI not only to perform tasks efficiently, but also to explain its reasoning, align with human cognitive patterns, and participate in collective knowledge building. This architecture supports applications in scientific discovery, autonomous decision-making, explainable multi-agent systems, and hybrid human-AI collaboration, demonstrating that UMT provides a scalable, cognitively grounded framework for next-generation artificial intelligence. In education, the unified metatheory of cognitive-symbolic systems offers a transformative approach to learning, moving beyond rote memorization to metacognitive skill building and reasoning development. Each layer of UMT corresponds to a specific cognitive competency. The consciousness relativity theory, CRT, helps students develop metacognitive awareness, enabling them to recognize their own assumptions, biases, and attention patterns. The differentiation reintegration theory, DRT, provides a framework for conceptual differentiation, helping learners form increasingly sophisticated mental models and abstract categories. Modular cognitive architecture, MCA, supports attentional control and integration, allowing students to manage multitasking, maintain focus, and engage in flow-state learning. The montage-based epistemic model, MEM, guides reasoning and knowledge construction, teaching students how to formulate hypotheses, evaluate evidence, and revise their beliefs systematically. The symbolic communication system, SCS, equips learners to communicate their understanding effectively through writing, diagrams, narratives, and symbolic reasoning. Finally, modular publishing theory, MPT, encourages collaborative knowledge creation, versioning, and peer review, giving students hands-on experience in building shared knowledge artifacts. Together, these layers form a coherent framework for educational design, one in which learners actively construct, communicate, and refine knowledge while developing cognitive flexibility, critical thinking, and collaborative problem-solving skills. UMT transforms education into a system where the learner's mind is not just a repository of facts, but an active participant in the generation and evolution of knowledge, preparing them for both personal mastery and participation in collective intelligence networks. In healthcare, the unified meta-theory provides a comprehensive framework for understanding and improving both individual cognitive processes and institutional medical practices. CRT allows clinicians to model perceptual biases and prediction errors that underlie conditions like anxiety, depression, and trauma, offering a pathway to early detection and tailored intervention. DRT helps explain how cognitive differentiation, or the lack thereof, can manifest in identity fragmentation, dissociation, or conceptual confusion, which is critical for developmental and psychiatric assessments. MCA provides a lens on integration failures, attentional lapses, and multitasking limitations, offering guidance for treating disorders like ADHD, PTSD, and schizophrenia through targeted interventions that enhance modular cognitive coordination. MEM supports cognitive therapy, belief revision, and narrative restructuring, enabling therapies like CBT, schema therapy, and narrative therapy to systematically transform maladaptive beliefs. SCS strengthens patient-clinician communication, ensuring that complex medical information is encoded, contextualized, and interpreted effectively, thereby improving adherence, informed consent, and shared decision-making. MPT extends these benefits to institutional knowledge, enabling hospitals, clinics, and research institutions to codify protocols, track case histories, and maintain versioned cultural knowledge for improved collaboration and consistency in treatment. Together, UMT provides a multi-layered, evidence-based approach for transforming healthcare delivery into a system that not only treats symptoms, but also optimizes cognitive, communicative, and cultural processes, fostering resilience and collective learning within the medical ecosystem. In governance and policy, the unified meta-theory offers a structured framework for creating transparent, adaptive, and evidence-based decision-making systems. CRT helps identify perceptual biases, misjudgments of risk, and framing effects among decision-makers, which is crucial for improving policy outcomes and reducing cognitive distortions in public administration. DRT provides insight into conceptual clarity and differentiation, allowing policymakers to model complex societal issues in hierarchical structures, improving scenario planning and strategic forecasting. MCA enhances understanding of attention, coordination, and integration across multiple agencies or departments, enabling effective multitasking, task prioritization, and stress-resilient governance. MEM supports hypothesis testing, policy reasoning, scenario modeling, and evaluation of competing theories, offering tools for adaptive policy development that can respond to evolving social dynamics. SCS ensures that policies, reports, and legislative communications are structured, contextualized, and interpretable by diverse stakeholders, fostering trust and clarity in public messaging. Finally, MPT organizes institutional memory, versioned legislation, collaborative drafting processes, and interagency knowledge sharing, which ensures continuity, accountability, and cumulative learning in governance. Collectively, UMT transforms governance into a cognitive-symbolic ecosystem where perception, reasoning, communication, and cultural knowledge interact to produce more rational, transparent, and collectively intelligent policymaking. The power of the unified meta-theory lies not just in its application within isolated domains, but in its capacity to integrate insights across artificial intelligence, education, healthcare, and governance. By providing a consistent framework that links perception, differentiation, integration, epistemic reasoning, symbolic communication, and cultural publication, UMT enables cross-domain learning and adaptive intelligence. In AI, it guides the design of systems that are interpretable, theory-building, and capable of collaborative knowledge creation. In education, it structures metacognitive learning, reasoning, and communication skills that scale from the individual to group-level knowledge construction. In healthcare, it supports diagnosis, cognitive therapy, and institutional memory of patient care, improving outcomes through structured understanding of consciousness, beliefs, and communication. Governance benefits from this integrated approach by aligning perceptual accuracy, reasoning, communication, and institutional knowledge into adaptive, transparent, and evidence-based policy. Looking forward, UMT opens the door to large-scale simulations, predictive models of cultural evolution, and hybrid human-AI knowledge systems. By operationalizing each of its 6 layers, CRT, DRT, MCA, MEM, SCS, and MPT, researchers and practitioners can empirically test, refine, and expand the theory, generating new insights into consciousness, learning, collective intelligence, and societal progress. Ultimately, UMT is both a conceptual lens and a practical toolkit for understanding and shaping complex cognitive-symbolic systems in the real world. Building on the theoretical foundations of UMT, the next crucial step is empirical validation and simulation. Each layer of the theory, CRT, DRT, MCA, MEM, SCS, and MPT, offers concrete, testable predictions that can be explored in neuroscience, psychology, artificial intelligence, and sociocultural studies. CRT can be evaluated through neural measures of prediction error, perceptual stability, and attentional modulation, providing insights into how conscious perception operates under uncertainty. DRT's hierarchical differentiation can be tested through developmental studies, neural feature maps, and unsupervised structure learning in AI. MCA's integrative processes lend themselves to investigation via global workspace dynamics, EEG/fMRI measures of modular integration, and multi-agent attention-based simulations. MEM's epistemic reasoning and belief revision can be modeled computationally in theory-building agents, neural symbolic reasoning frameworks, and scientific discovery simulations. SCS allows empirical studies on symbolic communication, natural language processing, and context-sensitive interpretation, while MPT provides a framework for observing cultural evolution, knowledge versioning, and collaborative systems in both real-world data and simulated environments. By running large-scale multi-agent simulations, researchers can observe cross-layer interactions, emergent consensus, hypothesis diversity, and information propagation, allowing the theory to generate actionable predictions and refine itself iteratively. These simulations transform UMT from a conceptual model into a living, testable system capable of learning from both human and artificial cognition. One of the most powerful aspects of the unified metatheory is its ability to model not just individual layers in isolation, but the interactions between them, revealing cross-layer dynamics that are essential for understanding cognition and culture. CRT's predictive perception interacts with MCA's modular integration to shape attentional prioritization, allowing agents to focus on relevant information while ignoring noise. MEM's epistemic reasoning depends on inputs from MCA and CRT, influencing how hypotheses are formed, revised, and blended across contexts. These hypotheses then feed into SCS, which translates internal knowledge into symbolic messages that can be shared, interpreted, and refined. Finally, MPT captures how these messages are stored, versioned, and propagated across populations, creating feedback loops that reshape cultural priors and influence perception, learning, and theory building in the next iteration. Practically, this means UMT can inform AI design, guiding the creation of systems that are self-monitoring, interpretable, and capable of collaborative learning. In education, it provides a roadmap for metacognitive skill development, teaching students not just content, but how to integrate perception, reasoning, communication, and cultural collaboration. In healthcare, it offers a structured approach to diagnosing and treating cognitive and integration disorders by mapping specific deficits to UMT layers. In governance, it enables transparent, adaptive decision-making through layered reasoning, symbolic communication, and institutional knowledge management. Cross-layer insights allow us to model emergent behaviors, predict collective outcomes, and design interventions that operate across cognitive and social systems simultaneously, making UMT a comprehensive tool for both understanding and shaping intelligent, adaptive systems. To illustrate the practical power of UMT, consider its application in artificial intelligence. By implementing CRT, AI systems gain uncertainty-aware perception, producing outputs accompanied by confidence scores and prediction error signals. MCA enables these systems to integrate heterogeneous inputs, coordinate multiple modules, and prioritize tasks effectively. MEM equips AI with the capacity for hypothesis generation, analogical reasoning, and belief revision, allowing it to construct, evaluate, and refine explanatory models. SCS ensures that these internal processes are translated into human-understandable symbolic explanations, supporting transparency and interpretability. Finally, MPT allows AI systems to share, version, and collaboratively refine knowledge across agents or even organizations, supporting collective intelligence and adaptive learning at scale. Case studies include scientific discovery systems where AI proposes and tests theories, education platforms that adaptively teach metacognitive skills, and healthcare diagnostics where AI interprets complex patient data while maintaining explainability. By integrating all 6 layers, UMT-based AI does not merely react. It reasons, communicates, and participates in cultural knowledge formation, bridging the gap between machine cognition and human understanding. These implementations highlight how UMT's theoretical insights translate into actionable designs, enabling intelligent systems that are not only functional but epistemically aligned with human cognitive and social processes. Looking ahead, the unified metatheory opens expansive avenues for both theoretical and applied research. In neuroscience, UMT invites studies probing how CRT, DRT, and MCA interact in real-time brain activity, using neuroimaging and intracranial recordings to validate predictions about attentional gating, hierarchical differentiation, and modular integration. In psychology, UMT suggests experiments on belief revision, narrative comprehension, and metacognitive learning, providing quantitative frameworks for understanding how humans process, communicate, and integrate knowledge. In artificial intelligence, UMT points toward the development of hybrid human, AI systems capable of multi-layer reasoning, explainable decision-making, and collaborative cultural knowledge building. Beyond individual cognition, UMT also frames collective intelligence. MPT allows us to model cultural evolution, collaborative research ecosystems, and information propagation across social networks. Philosophically, UMT challenges us to rethink consciousness, epistemology, and the social dimension of knowledge, providing a unified lens through which perception, reasoning, communication, and culture are interconnected. Ultimately, the horizon of UMT is not just about building smarter machines or understanding the mind in isolation. It is about designing systems, societies, and institutions that amplify human understanding, foster collective insight, and enable knowledge to flow seamlessly between individuals, communities, and intelligent systems. The theory offers a roadmap for experimentation, implementation, and ethical integration, suggesting that the next frontier of cognition is not merely personal or artificial, but profoundly interconnected and systemic.